Hi guys, so I'm going to walk you guys through the Unit 3 Part 2 practice test. I'm making this video from home, as you can see. So let me share my screen. Okay. So number 1 says a weather balloon contains a mixture of a gas and an initial volume. So as soon as you see a word like initial or final, that's how you know that you're going to be using PV over T equals PV over T. Gives you some conditions to prepare for the ascent to the atmosphere. The balloon is reduced in volume. So we see a change at constant temperature. So since the temperature doesn't change, that means that we're just going to use PV equals PV. We don't need to use the temperature. It doesn't change. Okay. So the initial pressure is 1. The initial volume is 600. You do not need to convert those into liters because it's going to be milliliters on both sides. And that's going to equal X, the pressure that you are solving for, and then multiplied by 50. Okay, so we're going to divide each side by 50. Okay. And if you do that, you should get 12. And the units for that is going to be atmospheres. Okay. Let's move on to number 2. What mass of CO2 gas exerts a pressure of 900 millimeters of mercury in a 200 milliliter container at 330 degrees Celsius? So whenever you are given mass and you are given the compound, then you know moles, right? Because you can go, whenever you get moles from PV equals nRT, then you can get mass from that compound using the molar mass. Now, we can solve for moles using the only equation that has moles in it that we've learned about in this unit, which is PV equals nRT. Okay. Now, the annoying thing is all of the variables that are given to you within this equation are all in the wrong units, right? So we're not allowed to use milliliters of mercury. We have to use atmospheres. We have to convert this into liters, which is easy, right? Because we just move the decimal place 1, 2, 3 places over. So it's 2 liters. And then for 30 degrees Celsius, we're not allowed to use Celsius. We have to use Kelvin. So we are going to add 273. So that's going to equal 303.15 Kelvin. Okay. To convert millimeters of mercury, I'm going to do that over here. Okay. So we have 900 millimeters of mercury. And if you look on your red paper, you're going to see that for every 1 atmosphere, there are 700 millimeters of mercury. So if we divide that up, then we are going to get 1.18 atmospheres. Okay, so now we're ready to plug everything in. So we have 1.18 multiplied by the volume of 0.2 equals X is what we're solving for, 0.08206. Right, whoops. Those two numbers are flipped. Whoops. And then multiplied by our temperature in Kelvin, which is 303.15. Now, you're going to multiply, or you're going to divide everything next to X. So that if you do that, then you would get, so X is going to equal, it's a pretty small number, 0.009487 moles. Okay, of course, it asks for grams, so we're going to go from moles to grams. Okay, do that. So for every 1 mole of this, my molar mass of CO2 is 44 grams. It's actually 44.01 grams. Okay, if I multiply that out, sorry, it's getting a little messy, then it's going to equal 0.417 grams of CO2. Okay. Number 3, what is the wavelength of a wave with this amount of energy? I know it's energy because the units are in joules. So in order to do this, I need to use both equations, C equals lambda mu, or I need to use substitution, just use the one equation. I'm going to use both equations. And E equals HV. Okay. The reason for that is we want to solve for frequency first. And then once we get frequency, we can plug it into here. Oh, wait, I said that wrong. So we're going to solve for frequency in this equation first, and then once we get frequency, then we can plug it into this equation and solve for wavelength. Okay, so they're kind of opposite sides. But anyway, this is my energy. So I have 1.834 times 10 to the negative 13. This is always going to be a small amount of energy because it's just a photon, right? So it's not going to, it's tiny, so it doesn't have a lot of energy. Equals 6.626 times 10 to the negative 34 times X. Okay, so if I divide both sides by 6.626, then X is going to equal 2.7 2.7, I'll just round, times 10 to the 20th per second or hertz, right? So that's my frequency. Now I can plug it into this equation over here. So C is the constant, so it's 2.998 times 10 to the 8th, and that's going to equal my wavelength, okay? Multiplied by my frequency, which is what I solved for, which is 2.77 times 10 to the 20th, okay? But if I divide both sides by this number, then X is going to equal 1.08 times 10 to the negative 12th, and the units of wavelength are meters. Okay. Number 4, which gas, F2 and OF2? So this is what F2 looks like. And then OF2 is going to look like this. Okay, it's going to be a bent structure. Okay. So which one is going to behave more like an ideal gas at low temperatures? Justify your choice. Okay, so we want the one that's smaller and the one, and the one that has weaker intermolecular forces, and this is both of those, right? So the correct answer is F2 because it is smaller and has weaker intermolecular forces. Okay, it only has London dispersion forces. Okay. So it behaves more like an ideal gas. Since its volume, you can say negligible is a common word to use. I mean, you could use other words like doesn't count or isn't as significant. Negligible. Ooh, how do I spell that? So it's volume negligible, and it is not very attracted to itself. So that's why it's more like an ideal. Moving over back. So we have this long explanation, just to go to the question here that says, determine the concentration of CuSO4 in the solution. So we are given the volume. That's not going to be relevant for this part of the question, but we are given the absorbance is 0.3, and we're also given a graph, right? So if the absorbance is 0.3, if I go over to the line and then down, I can estimate a little bit over to the right, that's going to be, I also have a concentration, okay? And that's the whole thing. So I don't need to use an equation at all. See, it's a whole lot of writing just to say, what is the concentration? So you're literally just reading the graph, okay? So you would just estimate, you would say 0.15, and then the units of concentration are molarity. That's it. You're literally just reading the graph, okay? Letter B, it says calculate the number of moles of CuSO4 in the impure sample. So we know that molarity equals moles over liters. We have molarity, we have liters, right? We have 100 milliliters right here. So we can solve for moles. So we're going to have 0.15 is going to equal X over 0.1. So if I multiply both sides by 0.1, then I'm going to get 0.015 moles. Okay. Number 6, this is the one that's the same as your homework. Whoops. So we have a spectrometer with a path length of 1 centimeter. We have this wavelength. This is not relevant for the problem, and the absorbance is 0.4. So if I go to 0.4 and then I go down, the concentration is 2.5. So I'm going to be using the equation A equals EBC. Okay. I'm solving for the molar absorptivity. That's what it asked me for. And I know that the absorbance is 0.4. That's going to equal X times 1, which is the path length, times my concentration, which I found on the periodic table, the graph, as 2.5. Divide both sides by 2.5. Then my E, my molar absorptivity, is going to equal 0.16. And then the units for that is M-1, Cm-1. Okay. Last one says find the concentration if the absorbance was this. So you assume that this is still the molar absorptivity constant because it's the same compound, right? It's just letter B of this question. So I'm going to use A equals EBC again. Okay. So my absorbance is given to me as 0.684, and that's going to equal my absorbance, molar absorptivity is 0.16. Path length is still the same, and then I would just divide both sides by 0.16, and my concentration is going to equal 4.275 molar. Okay. Hopefully that was helpful. Casey, ready? Introduce you to my dog. You want to see my students? Say hi. Hi. Yes. They're like, why didn't I get food? Okay, bye.